Yeah.
Okay, I think we'll get started. It's my honor to present our speaker today, Professor Josh Garcia. Professor Garcia does research in the areas of, software testing and analysis broadly and more specifically towards autonomous vehicles. He also has a body of work on architectural erosion, on just the software analysis itself, and several other topics. He's also been responsible for creating a lot of tools that researchers across the world are using to conduct their research. And I think that's all I can, I've got. This is a surprise introduction. So with that, I will let Josh tell us about his work.
Awesome. Thank you so much, Jim, for the Thank you for the clap. So I'm going to start by telling you more about the Software Aurora lab that I head and run. And so over at the, and that needs to go away. Okay, so in Software Aurora lab, we do automatic software analysis. In particular, we analyze different program properties in software systems so that we can find things like bugs, for example, which include vulnerabilities. But also, as Jim said, whether or not your software system is decaying or eroding, for example, and to do that, we empower our techniques with a variety of different things. In particular, program analysis of two kinds, the dynamic kind, where you actually execute the system to get information. Also the static kind, which basically acts like a compiler. You don't have to actually execute the system. Scalable design is very important to me, so I try to get our work to always include that in some shape or form. And yeah, AI and machine learning is really hot right now. My group and I have been working on actually mixing these AI and machine learning into software engineering for quite a long time, actually. And so besides that, we also inform our automated solutions with, for example, data mining techniques, often called mining software repositories in software engineering or empirical software engineering in general. But we're increasingly utilizing more qualitative methods like open coding, surveys, and interviews. Those are the methods. What are the problem domains? Before I tell you that, I'm going to rewind back a bit. And some of the students in my courses have seen this already. There will be a twist, okay? And hopefully some of the, let's say, more senior faculty, there's one of them in the back, will join in, okay? So I've actually been programming since I was 11, about the age of Bart, who was also perennially 11 like myself. These are standards. Who knows what standards are on a chalkboard? I know some of you do. Yeah, really? You never had to do anything like this? For your punishment, write what you shouldn't do over and over again on the chalkboard? Okay.
I didn't know they were called standards.
Yeah, so, okay. None of the software engineering students, when I asked, know this phrasing before. But I bet some of the software faculty could. Can someone tell me what that statement means before I have to?
Oh, go twos. Make spaghetti code, right?
Yes, exactly. Spaghetti code. So. Right. So go-to statements allow you to arbitrarily, for example, jump around structured coding constructs like functions, right? So they allow you to essentially wreck the structure of your system. And when I was 11, when I was looking at basic code on a machine, I was reading through go-to statements and like going kind of nuts, like what is this all about? And I thought there was something wrong with me. No, all the way back in like, what is it, around like 60 or 70, one of the famous Turing Award winners was already telling us to stop doing that. Okay. I used the internet before it was popular. Okay, again, none of my students know what these are. Can someone who's maybe older tell me what this is?
It's like an internet provider.
Yeah.
Yeah, it's the first big internet provider out there that like was for mass consumption. Okay, I used to use CompuServe, and luckily my family got that for me. But by the time I was spending $200 per month on the internet, they cut that off for me. Right, that's like $300 to $500 nowadays. Right, you probably do that for your kids too, right? So I instead started taking my modem and connecting to one of these. Does anyone know what that is?
Bulletin board.
Yeah, bulletin board system. Yes, finally, someone who relates. And how does these work? Jim, can you tell us?
You would dial up on your modem to your internet service provider, and now you're on the internet. And then you were like, there wasn't anything on. There was no web yet, so like there weren't any. So somebody would be running one of these things on their own computer. And then you could have like a little community, you could talk to each other, or you could like play games or whatever that particular BBS supported. And everything was text-based because we didn't have graphics in those days, or very rudimentary graphics where the characters are blocks, basically.
Absolutely. So I would connect to one of these to get my internet, to meet people online, including the server admin who would message me, and I'd be like, yeah, I'm a kid and don't worry, nothing bad happened to me. But like, that's how I started getting my internet back then. Okay, so hopefully you can tell I'm a nerd. I love science. As a kid, I would be asking, so it's the holiday season. I'd be asking for things like chemistry sets, anatomy of the body, and build those kinds of things. Big nerd still am. Okay. All right. Now you're probably getting some sense that I'm vain. I drove 170,000 miles to get my college degrees. That's about 4 or 5 times the circumference of the earth. Okay. We'll get back to that. Okay, college challenges. Some of you can relate to this, especially the students, right? We're coming from like low income families and gang ridden neighborhoods. So for instance, so now I really care about getting and protecting my assets and not being attacked and defending myself. Okay, why am I talking about this? Remember we were talking about the problem domains? I work in 3 key problem domains. Please help me, tell me what they are. You probably heard someone say it earlier. This one would be
Driving.
Yeah. Plus my dad worked 28 years at the DMV. So like I talked a lot with my dad about that, about non-autonomous driving. Okay, I want to protect my assets. I want to defend myself. Security, yes, exactly. And go-to statements. I don't like those. So instead I like
Structured programming, architecture.
Exactly.
Good architecture.
Exactly. Okay. All right. Today's talk is focused on what my group and I have largely been focused on for the last several years, which is autonomous driving. Okay. So, autonomous vehicles, hopefully this isn't too hard to motivate to you. They're becoming increasingly ubiquitous and pervasive. Plenty of companies claiming millions of miles driven nowadays. And of course, you don't want faults and defects in these things, right? They're safety critical. Collisions kill people or living creatures, like maybe pets, which is something special for me. Anyone remember this here at UCI? Okay, who doesn't remember? Who has never seen these around UCI? All right, yes, these autonomous vehicles used to pick up students, maybe faculty, drive them around the UCI campus. There's at least 10 of them in their fleet. What happened to them? I'll tell you. Hold on. These kinds of things. So very sadly, in Tempe, Arizona in 2018 was the first fatality due to an autonomous vehicle operated by Uber. So that took Uber out of this game for a long time. What happened to bot ride, pony pilots? After a series of accidents, one of their vehicles hit a stop sign in Fremont, and they lost their permit to operate. Okay, start again. GM Cruise, fall of 2023, year ago, in San Francisco. Dragged a pedestrian around 20 feet. Hospital for months, terrible. Okay, and now Waymo's all over LA. They've been in San Francisco. These things are going everywhere. It'll be interesting to see how Waymo reacts to their first big accident. Okay, with that said, I've told you a little bit about my lab and myself, motivated autonomous vehicles. I'll talk about our studies and solutions in that space. And then I will conclude and say our fond farewells. All right, let's get into it. Let's get into one of the first studies I did on autonomous vehicles, which is basically understanding the nature of autonomous vehicle bugs. And prior to that work we did around 2019 to 2020, there were no previous empirical studies of autonomous vehicle bugs. Nobody had a great understanding of their classification, in particular in terms of their root cause, driving errors, driving symptoms, parts of the AV system affected, particularly the components. So to that end, and really for the rest of the last several years, we've been focusing on two open source, widely used, popular industrial grade autonomous driving systems, or ADSs for short. Baidu Apollo and AutoWare. Apollo, besides having production agreements with Volvo and Ford, has been deployed and driving public passengers in a variety of cities in China, including Wuhan. AutoWare, which is operated by the AutoWare Foundation and largely supported by a company called Tier 4, we're part of that foundation actually, has about 30 different companies and universities behind it. Okay, so what we did is we studied about 500 bugs starting from around 16,800 commits. And we found a variety of these root causes, bug symptoms categories. And then we provide some actionable insights to researchers and practitioners in the software space. To better appreciate the rest of this talk, it's good to understand the software architecture of a typical ADS, like the two that we just talked about. So they have a bunch of sensors that are used to identify the location of the vehicle at any point in time, the objects around them and track it, or track them rather, predict the future trajectories of those obstacles, possibly with high definition map information, and then plan to trajectories that a vehicle is going to drive at any point in time, which are translated into low-level control commands that are sent through CAN bus to control steering, braking, and acceleration. And then there's other aspects like more of the GUI interface called the human machine interface here, and some infrastructure coding components. So for this study, from that, recall 16,800 commits, we focus on close and merge bug fix pull requests, giving us 500 bugs to study over the entire lifetime of these open source systems up to that point. We ended up with this taxonomy of 13 root causes, 20 symptoms, 18 components. And we studied a bunch of research questions with respect to them, but I'm only going to briefly focus on one for this part of the talk, the frequency of bugs in these ADS components. Let's take a look at that. So we have these components. What are the most buggy? Well, some of them are these. A lot of work has been done studying perception, this computer vision oriented component with a lot of machine learning in it nowadays, or especially back then. But guess which ones are most buggy? Not those. This, and in particular, the planning component. So for the rest of our studies, we focused on this most buggy planning component. And one of the reasons beyond it just being so buggy is that it actually affects, to a large extent, a lot of the driving functionality, 62% of them. Okay, so now you have a better understanding of the nature of these ADS bugs. let's look into the techniques that we produce to help find these bugs and get some quality assurance of these autonomous vehicles. Before we do that, it's useful to know a little bit about the background of ADS testing. There's at least two different kinds. Field operational, so you take an actual physical AV, you drive it around the world, or the real physical world rather. And of course, that's risky. Real world collisions can cause serious damage. But on top of that, it can be quite inconvenient because getting these permits or licenses is not that. So we focus on simulation-based testing. Doesn't require a permit, but we have this challenge of testing being realistic, the sim reality gap, as it's often called. Prior to our testing techniques, these are the most state-of-the-art approaches out there. They focus on collisions, but they have some little limitations. So for example, they only generate scenarios with a single AV and a few obstacles. But even worse, we can ask a more important question. For all these collisions or other violations, do they really cause bugs? And here, I'm gonna ask you to help me out. So this scenario, the red vehicle is the AV and the yellow vehicle is an obstacle. And this happens. Who do you think is responsible for this collision? Anyone?
Green.
Anyone?
It's a toss-up, right?
What was that?
Toss-up?
It's a toss-up?
Not if the yellow car also has a green light, then it must yield to the red car turning left. You can't turn left into oncoming traffic.
So under California law,
You
which is
can.
where most of the testing goes on here, the obstacle has the right of way. This does not. In other words, under California law, the autonomous vehicle is always responsible, and thus it's buggy.
Oh.
Okay, let's try another one. Okay, now we're gonna have autonomous vehicle, just driving straight, an obstacle behind it, and bang. Okay, given maybe those clues there, and particularly, let's look, California law,
The AV's always responsible?
if it doesn't have right of way.
Oh, so then it's the yellow car.
Yes, it is a yellow car.
Don't rear end anyone.
So, yes. So in that case, Waymo, GM Cruise, whoever would not be responsible. So this responsibility aspect is a big deal into determining whether or not an ADS is bug related. So to determine responsibility, someone, namely one of my PhD students, Yuchi, went through this hard task of studying responsibility. Okay, so some of you have seen this already. Some of you know Yuchi. That is literally how Yuchi looks like. If you want to play Where's Waldo, you can look around a bit and try to identify him. So Yuchi would go to speak with police officers, insurance investigators. Well, not insurance investigators, police officers, but he would study up insurance investigations. And a lot of this responsibility is determined by courts and lawyers. And so determining responsibility using what we call this experts on call method can be very cumbersome, slow, manual. So we call that a naive approach. We don't want to do it that way. So maybe we can do it in a different way. Maybe we can get some sophisticated model that follows all of these driving rules and right-of-way laws and somehow can never be responsible for a collision so that if one occurs with an autonomous vehicle, the autonomous vehicle is responsible and thus buggy. Okay, is that what we did? Probably not, because we call that approach naive, but we have something like this already, right? For those of you already seen some of this, don't spoil it for the rest. What do we have already potentially that might?
Data from reality.
We do have that, so more people are using that, yes. We also have something else. Video games actually are provide a lot of inspiration for testing these things actually. Okay. We have the ADS itself. What? Okay, so what we can do to guarantee responsibility is drive a bunch of autonomous vehicles together in simulation, and whenever a collision occurs, autonomous vehicle is always responsible. But challenges arise, in particular, not only is running multiple autonomous vehicles very expensive, just driving one in simulation is expensive. Existing simulators don't even support multiple autonomous vehicles, at least for these like industrial grade, high autonomy, open source autonomous vehicle systems. And so what we did is we created this doppelganger testing, doppeltest for short, that operates as follows. It parses an HD map to help generate some scenarios using an evolutionary or genetic algorithm. And then in place of these external simulators that don't handle multiple AVs, we created this doppelganger orchestrator. And then from the recorded scenarios we use there, we pump this information to an analyzer that identifies violations and other information to help produce more bug revealing scenarios. So the map parser here is particularly interesting because unlike previous techniques, it would actually control traffic lights in a realistic manner to maximize very hard to obtain violations like running a red light for an autonomous vehicle. The scenario generator models the autonomous vehicles, pedestrians, this traffic control we were talking about previously. And this doppelganger orchestrator aims for realism, efficiency, and sharing information among the autonomous vehicles in place of simulators that don't handle multiple autonomous vehicles. And this analyzer, as I said, identifies a variety of different violations, but in particular, one of the interesting things we found is just maximizing the number of unique decisions actually reveals a good amount of bugs. Okay, so to assess doppel test and see how good it is, what we did is we ran 240 hours of experimentation on Baidu Apollo on a street in Sunnyvale, California, called Bregas Avenue. This picture, Yuchi actually went to Bregas Avenue in Sunnyvale and took that picture. And that's what you're seeing now. Thank you, Yuchi. Okay. And we found a variety of interesting different types of bugs and bug instances, 8 in total. I'll focus on one particular case study involving an unsafe lane borrow with these 3 AVs, which operates as follows. So at the beginning, this blue AV decides, okay, I want to go around this AV in front of me, so I'm just going to drive around it. Okay. And then later on, these 2 vehicles see each other. This sees that vehicle and tries to drive around it. This one's still moving forward. A collision is going to happen. Can you guess what's going to collide with what now? Anyone want to guess? I know some of you have seen this already, so you might know already from that, but again, if you haven't, I'm particularly interested to hear what you think will happen. Yes, Eric.
Look, I'm gonna make all the wrong guesses, but are red and blue both gonna swerve and hit each other?
That's a good guess. What actually happens is this vehicle yields, this vehicle drives forward, and then
All 3 of them crash.
they do try to drive around each other, but ultimately these 2 end up hitting each other. Yeah, a bug revealing collision. Beyond that, we're able to find some interesting traffic control, traffic signal, stop sign oriented bugs like running a red light here. Those are extremely hard to find. And we were also fortunate to be able to get 3 of our bugs confirmed. One of our fixes submitted and accepted. It's very difficult to get Baidu to accept any confirmed bugs or fixes.
Wait, you identified a bug in an actual AV that's in use,
Yes.
and then you submitted it and they fixed it?
Yeah.
That is awesome.
Yeah, thanks. And thank you to my students for doing the real work, if you will. So Doppel test was extra nice because we managed to get it through artifact evaluation. So you submit our artifacts, we get them to use it. These are very hard systems to install and use. They require a lot of resources to even run. As far as we're aware, we're the first of autonomous driving testing approach to make it through artifact evaluation. Okay, so we moved from violations to bugs. But clearly there's some constraints here that reduce diversity, right? Not all obstacles, not all vehicles, autonomous vehicles, for example. So we created another technique called Senorita. What are some of these challenges? I've already been hinting at the expense of the hardware resources for Doppel tests. And I've also talked a little bit about how these external simulators, like the SVL simulator from the big South Korean tech company, LG, impose constraints on testing. In particular, given the design of these external simulators, previous techniques actually required a big amount of manual specification of these scenarios. So you'd have to somehow specify a bunch of these attributes, position, speeding, velocity. They can be lengthy, they can involve hundreds of data points. And so you get these, what we call immutable scenarios. Basically, you have the same scenario happening over and over again. On top of that, the simulator or the bridge between the simulator and the autonomous driving system itself can be buggy. So for instance, we have a pedestrian here in the simulator next to the vehicle. The autonomous driving system doesn't even know it's there because of these simulator or simulator to ADS bridge bugs. And even worse, a lot of these previous techniques would rely on this simulator that got shut down by LG and is no longer available, except, again, I guess Yuchi maintains a version. Okay, so how do we overcome these restrictions with respect to manual specification and external simulator so that we can get these diverse scenarios? Well, Senorita does it by taking these domain-specific constraints with respect to obstacles and all sorts of other scenario elements, which Sumaya worked extensively on. We're still using these evolutionary genetic algorithms to produce these scenarios, run them, record them, and find different kinds of safety and comfort violations and identify unique ones, reduce duplicates. I'll focus on two particular components for Senorita: scenario generator and the player of the scenarios. So the scenario generator is pretty interesting because since we're not relying on an external simulator and built-in simulators don't generate the trajectories for you, we do that using state-of-the-art planning trajectory algorithms like Stanley Control. And given the domain-specific constraints and trajectories, we represent these obstacles using these genetic representations and genetic algorithms. So an obstacle is an individual, but there are limitations to this representation in previous work that make the individuals immutable. So for example, for an obstacle, the fixed sizes are specified and constrained by the simulator, and you can't really change them easily because they're 3D models that aim to be realistic and, again, not easy to mess around with. These are just manually specified start and end positions of a particular route to be followed, again, because of the external simulator. So these previous techniques end up only being able to do things like change the speed. Because Senorita aims to be fully mutable, again, through these domain-specific constraints and automatically generated trajectories, Senorita makes the whole thing flexible. But on top of that, we also leverage a concept in genetic algorithms that, as far as we are aware, was not utilized much, which is these concept of deems. Okay, anyone here who has not worked on Doppel tests know about deems or has not seen Doppel tests before? Okay, good. So it's still the case that doesn't seem to be made aware of much, but genetic algorithms have this concept of deems where you have an entire population of individuals that you want to evolve over time. The deems are subpopulations. And so through using that concept, we can have a nice representation of obstacles and individuals, deems as scenarios, and we can add and remove obstacles quite elegantly using this representation. But on top of that, we can do the typical kinds of genetic operations you see in these algorithms, like, for example, within a deem, within a scenario, crossover obstacles, copy over one obstacle in one scenario to the other, mutate one of the obstacles already in that scenario, or just mute out like the entire obstacle or even just a part of it. Since we're losing that external simulator, we need to simulate somehow. And so we do things like route information to perception to simulate localization. We use built-in mechanisms like the sim control to replace the control module. This comes from Apollo itself. And this ends up in a very efficient, flexible technique that hopefully you can see here blows the other ones out of the park. Senorita has about 163 times more bug revealing violations than A/B fuzzer, about 30 times more than autofuzz. Why? Well, because of things like this. We have these flexible trajectories that in previous techniques, they're just look like this, just driving the same way over and over again. Senorita can drive everywhere and like get into all of these interesting, challenging scenarios. And techniques like A/B fuzzer would just like do this over and over and over again, where the blue vehicle is like, I have right of way. Yeah, I'm driving. And the red vehicle's like, I don't care. I'm just going to run into you over and over again. Okay. So now what we're going to do is move to a different input space, a meta level, if you will, this exponential configuration space, testing space that is hard to test called conv. Right, so what does a configuration mean here? Configuration is a set of options and their values. Every option you could think of as a key value pair. So for instance, this configuration file has an acceleration weight that you can adjust and you make it arbitrarily large, right? And you can and that can give you what's called a misconfiguration, which could be buggy or vulnerable. For the two systems we've been focusing on for years, there are thousands of configurations, like 2,000 for Apollo, 2,500 for hardware. And actually to test these configurations would be dealing with an exponential explosion in configuration. So just take one of the basically state-of-the-art, but very simple testing techniques where you test pairwise combinations of, in this case, Apollo. You get over 1.8 million combinations to test. On top of that, you take 1,000 scenarios to test with those configurations at 30 seconds each. 30 seconds is the typical time to test one of these scenarios. You will be testing for 1,800 years, and big tech companies are certainly not waiting that long to put autonomous vehicles on the roads, right? There's an important concept that we want to share with you that we call emerge violations in this configuration testing space. Given a default configuration, if we tune the value, get an alternative configuration, and we want to find violations we haven't seen before from the default configuration, which we call the emerge violations. Previous ADS testing techniques only test the default configurations, even though about 27% of bugs in these ADSs involve incorrect configurations, as we discovered in the initial study we talked about at the beginning of this talk. So let's test those alternative configurations. To do that, a test case is no longer just a driving scenario, just to make it clear. It's a driving scenario plus a configuration. And because all of this is getting much more expensive, we have to simulate and test and do this for so many different configurations. We want to reduce that testing time somehow. And to do that, we try to, or we manage to avoid violations or failure masking, where one violation or failure hides another. So for example, in this default configuration, spend more time here. You'll have this scenario. One vehicle overtakes the other. If we tune one of the options to a particular value, the same scenario can result in this collision. If we only tune this option but not that, the vehicles can just freeze there. If we take both of these options and their respective values and test them together, the vehicle still freezes. In other words, this tuning configuration masks this. We want to avoid that. To that end, conf.ve takes these default configurations plus scenario generators like the ones you saw before, Senorita and Doppel test, and uses their initial scenarios and violations, removes duplicates, performs something called a range analysis, which I'll talk about more, which is also very important for avoiding masking failures and violations. With that information plus the default configuration, this configurator, another evolutionary algorithm, produces alternative configuration, which we execute to get these alternative select scenarios, filter out duplicates, and get these unique emerged violations, along with their suspicious configurations, which can be used to identify locations of faults and repair them. So oracles, which in a test tells you whether or not your test passes or fails. We have these safety and comfort violations, which we talked about to some extent before. What's particularly new here in conf.ve are these new oracles that are focused on module level failures. For the configuration, since we're testing differently, individuals are simply configurations in this genetic representation. So genes are just options and their values. To go a little bit lower in detail, the fitness functions, the objective functions, the goals we want to maximize. Some of them are similar to previous work. One of the particularly interesting ones is the sinuosity function, which represents the shape of the planning routes or trajectories. It actually makes a big difference in this setting. And now, how do we handle violation masking or failure masking? Well, one of the simple things we do is we realize that Yuntani, who led this work in particular, realized that the same module violation will occur over and over again and prevent scenario diversity. So we don't want to select module violations for future evolution. But in terms of a more sophisticated solution that helps a lot is we create this dynamic range analysis where we identify valid and invalid option ranges to reduce violation masking, identify invalid configurations. In other words, we want to know what the valid upper and lower bounds are of option values. And we can't do that using static analysis because these systems don't statically guard or write their valid ranges in there, whether it's documentation or in the code. So to narrow down the valid ranges, we take, for example, a representation like this, where we have, for example, a default option value, and then we start with an arbitrary lower value and a large upper value. And then we leverage the insights that the default range is likely to be within a valid range by default. And these failure ranges tell us more or less where the minimum or maximum values are for these options. In other words, given this scenario where a failure occurs between the default option and the original upper bound, any values greater than this failed value are likely to be invalid, so we can cut that off. Similarly, for the lower bound when we find them. And through this And through this relatively simple, but I think insightful design, we actually identify the valid ranges. And over time, this actually speeds up the testing and finds more diverse scenarios. So how does ConfVE do in actual experimentation? Well, we did a lot of experimentation for ConfVE. Over about 125,000 virtual tests and 990 hours of tests. That's about 41 days long worth of testing in wall clock time at least. And we compared against state-of-the-art algorithms. There weren't any others for autonomous driving, so we selected configuration testing algorithms, not specifically for autonomous driving, like pairwise testing and ConfVD. And one day we'll do ConfV F to Z. Okay, that one didn't hit, huh? Okay. Again, we're focusing on planning. So for both Apollo and AutoWare, we tested hundreds of different options and their variety of different value types. For Apollo specifically, we took the previous techniques, some of them you've seen already, run them on a variety of different maps in California. Why in California so much? Because a lot of the ADES testing actually occurs in California, where we are. And then for AutoWare, there aren't that many, really aren't any at this time when we were doing this, scenario generation techniques, but we were lucky enough to be able to get the test from the actual CI/CD system or AutoWare evaluator. Tier 4 was kind enough to share that with us. They run on these particular HD maps. So overall, the results look like this, and ConfVE actually finds 27% more unique bug revealing violations, these emerge violations, than pairwise testing, and about 66% more than the D version of testing, ConfVE. Okay. What do one of these scenarios look like when you actually play them? Let's look at one, a collision on Borregas Avenue, where an autonomous vehicle is driving through an intersection. And a vehicle comes through, and here comes a bicycle, and here comes a pedestrian, and it's trying to yield and maintain a safe distance from the bicycle. And okay. Oh, and then decides to stop, and it's too late. Bam. It just hit the bicycle. What did it take for that to happen? All it took was a 15% increase in the max deceleration. And this was found using ConfVE. And so Yun-Tan and the team identified 4 different bugs across 2 different issues that they posted, and 2 fixes were accepted to AutoWare. Hooray. All right, we are reaching our fond farewells. I'll tell you more about some of the work that's going on now and we plan to do in the future. There's still a lot to be done in responsibility, actually. And actually not much testing, at least in the academic literature, is done in terms of collision avoidability. So can I avoid the collision like the one you saw before? As you can probably imagine, deep neural networks are being put into everything, including these autonomous driving systems. And there's this push to turn all of those components that we talked about in the architecture into just one big deep neural network. Some of these systems are doing that. They call it end-to-end. I'm not sure why they call it end-to-end. It's just one big deep neural network. And then there's this issue of non-determinism that's inherent in the cyber-physical systems that actually make it very hard to reproduce a test and repair the test, or even figure out where the bug originates in the code. Beyond that, I appreciate the fact that, for example, I think within the last year or 2, we actually had an autonomous driving talk here in informatics about the way workers are being descaled due to these autonomous vehicles. I'm not too happy about that. And actually, some people at the head of the AutoWare Foundation are not happy about that. And so, like, it would be great at the very least if we can reskill or upskill workers, not simply replace them. So for instance, not in autonomous vehicles, we have this ongoing project called Code Safe, where we're building an educational platform for software security to help reskill and upskill low-income workers, for example. But beyond that, I think there's aspects not related to safety that are still very important and ignored. So, for example, motion sickness, I think, is a big deal in autonomous driving. 30 to 40% of the population suffer from motion sickness. Most of that subpopulation are women. So, I'm not so sure how I would tackle all of this, but I think this is interesting and important, and I try to say these things, these particular issues, when I have an opportunity. Okay, as I round things out, I'd like to thank the department for helping me move all of these different types of research into different areas I focus on forward. I also want to thank people like Stacy here, Andre online, anyone else on these that are bringing me into areas I never necessarily thought I would be working with, whether that's accessibility or like hardware acceleration for software. I've been lucky to have the work over the last several years funded by a variety of different agencies or companies, or a few different agencies and companies, but more widely over the course of my career have lots of users and contributors to my research artifacts. Some of them maybe not so happy to know that, don't play so well together. I definitely have to thank my collaborators who do autonomous driving testing and have put a bunch of time and effort with me. And please don't actually call this phone number. It's not the actual line to the Sora lab. It's actually a line to somebody in chemistry. All right, and of course, I want to thank you all for your time, attention, and I'm happy to take more questions. Thank you.
So like since like 2016, I'd say maybe even before that, there's been a certain person who always says that we're 1 or 2 years away from autonomous vehicles or level 5 autonomous cars. And I'm wondering, you as someone who's educated in the field, where do you think we are in terms of eventually getting level 5 autonomy?
Certain person.
Quote unquote person.
Yeah, we had a talk about them not too long ago.
Oh my
For anyone
gosh.
who's not in on the joke.
That certain person is more indirectly involved in my life than you might realize, so I'm not gonna not in both good ways and bad ways. So I'm editing as I speak. So in terms of like how far we are away from like full autonomy, it depends on what you mean by full. Yeah, we can just put them out there and they'll drive. Will they drive safely? Will they drive in a way that doesn't make you just want to vomit all over the car? Will they be affordable? Like a Waymo vehicle costs about $110,000, $120,000 to maintain a year. I don't think any of the drivers right now, taxi or rideshare, are getting paid that much per year. So, I think that gives you an idea how far away we are at the moment. But thanks for asking. Sorry, go ahead, Stacey.
Yeah, so you gave the example of a 15%, being 15% off, and then that leading to for example, a bicycle accident.
Yeah.
When you fix that or recalibrate that, then does that introduce new bugs possibly? And do you check for that?
Yes, that is a great question. Oh, I really like that question.
Good.
So for
David, please off.
so let's say we find a valid range,
Mhm,
it would make sense to fix it in terms of that range. That's great.
mhm.
A big challenge, which a good number of us, particularly software testing professors here know of, is regression testing, right? What you mentioned. Will our fix actually introduce maybe another bug we never realized? Regression testing, there's been some research on regression testing for autonomous driving, but very little. And given just how expensive it is to run these tests, whether in simulation or in the physical world, yeah, that is very scary. Somebody should be working more on that.
Can I ask you a follow-up? So when do you decide to make the effort to actually put in a bug fix? And can you tell us a little bit about that process and the work you do with that?
Oh my gosh, my students can tell you a lot about that. So there is definitely, they're running a lot of tests. So at least they have some kind of test suite that they can rerun, and they do rerun like many times over. Well, that 990 hours is really a lower bound. They do way more testing than that. And so, in particular, so they're doing some kind of more manual-oriented regression testing when they submit a bug to be confirmed and fixed. But again, getting like some companies to take that seriously, let's just say, is not easy. You mentioned Tesla. I'm just gonna say Tesla out loud. So, Tesla has full self-driving, and which supposedly is one of these end-to-end systems with one big neural network. There's actually like a website and a Twitter page that tracks like people's reports about essentially all the bugs they're finding with that. So that's kind of a bug report. Are they confirming or fixing those bugs? I better stop there.
Think
Yes.
you already answered.
Can you, one thing that I was curious about is the role of open source in these sorts of systems, right? Like obviously everything that you're doing is dependent on open source. And you know, it's nice because, you know, it allows you to verify that these systems are working well. But I guess part of my question is, you know, a lot of the Western, you know, Tesla, a lot of the Western places are using entirely different autonomous driving systems that you have no access to. Are we, by relying on open source, just kind of lagging behind what they're doing secretly, or are their systems worse?
Oh, yeah, that's a great question. I feel like the answer is kind of both, which I know is not a very satisfying answer. In some ways, it's better because anyone can go in, and this is the argument that people made, for instance, when Android versus iPhone, which one is safer, less buggy, more secure, whatever. Well, iPhone's very closed system, trust Apple. Android, open system, at least lots of people are going in, and we know like that we have some like confidence that, you know, the public can see what's going on. So similar here. So AutoWare is deployed in like robo taxis in Japan, but they don't really necessarily like being called industrial grade, even though they're really being deployed in industry. I think, oh my gosh, I have to stop. I have to be careful what I say. I'll stop. So for Apollo, on the other hand, they're even more careful about that stuff. Big company. And I've heard things like, oh yeah, our open source version is not really our commercial version, which sounds like a great way to like deflect responsibility. Sorry, maybe we should cut some of this. But anyways, and then for companies, oh my gosh, okay, like Waymo.
Offline, recording.
Yeah, for like Waymo or GM Cruise, you know,